So welcome to this pre-recording of lecture 26 of Introduction to Symbolic Computation. This lecture is on two-dimensional plots, and there are many software systems out there that do an excellent job at two-dimensional plots and any dimensional, well, three-dimensional plots. Viewed as a problem in symbolic computation, we can also examine or transition into forms that are better suitable for plotting. So we will distinguish between four types of plots, starting from the explicit plotting of functions and the implicit plot. So these are the first two main categories of plots we consider. And then in the second part, I will show how when curves are given in parameter representation, that there the plotting goes a lot more efficiently. And this is also where symbolic computation comes in. Given a curve in implicit coordinates given by an equation, transform into polar coordinates. We will see an example. If you can transform to polar coordinates, then the plotting goes a lot more accurately and a lot more efficiently. Okay, let us look at a first example. Here we have a periodic function with a decaying amplitude. So this is a sine function which oscillates with the amplitude drawn here in red and in green. So these are three plots all in one. So the plot of the function is drawn in blue. The amplitude kind of gives additional perspective to this plot. We can compute plots and then render them. So in this way we can make very interesting plots from basic building blocks. But even already when we have an explicit function, y equals f of x, there might be difficulties. Here you see one of these problems. Without giving special directives to the plot might not be so interesting. Okay, so that was the plotting of functions. Now let's look at an equation. So any planar curve can be defined, or any equation in two variables defines in general a curve in the plane. So here we see a rather interesting famous curve, or a curve invented by a famous person dating back from the Industrial Revolution. So it's a curve of degree 6, here written in the equation form, which is not the best form to plot this curve. You may observe that the x equals 0, y equals 0 satisfies the equation. However, you see that the plot does not go through the origin. So we will see when we do the computations that the origin is an isolated point on this curve. So in plotting, we consider the real parts, and the real parts already can give for quite surprising facts that are counterintuitive to the geometry. So this is one of the examples. So one would expect that when you have one equation and two unknowns, there is 1 degree of freedom. So you have one nice smooth curve, but you may have, when you look at to the reals, which is the classical perspective, you see only a point, and actually you don't see the point. So we have to do a trick to display the point. Okay, so when curves are given in parametric form, they are much easier to plot and also much easier to define. So here is the class of Lissajous curves. So it's just one Lissajous curve. The parameter t, so there is one parameter that runs typically, as these are periodic functions, to 0 to 2 pi. We can change the frequencies, and you can also eventually swap the sines for cosines. So this is one instance of a rather already looking complex curve. So a curve, by the way, given by two functions in one variable. So this is an example of a curve in parameter form in a rectangular coordinates, so in coordinates x and y. One sees that when one makes plots with an implicit plot, one has to carefully often choose the range of the plot. Here, that is also already taken care of. So the range of x and y, because they are sines, we know that this plot will take values between -1 and 1. So for proportionality, the viewing window is already here defined. So when we go back to the curve invented by James Watt, when we present this in polar coordinates, and we will see a polar coordinate representation, or actually we will compute the curve in polar representation, then we can actually see that the origin belongs to the curve, but it is an isolated point. Also, that the green and the red, so these are the green and the red, the curve actually falls out in several parts. So the equation is of degree 6. So there are multiple parts in this curve, and with the parametric representation, one can choose a suitable range. So the green is done for one range of t, and the red is then done for another range of t. So one can further investigate the curve. The other point, and there are actually many points I want to make. So the first point I had to make was actually the polar coordinates. What we compute is a function that for any given angle, so we kind of run the angle here, and then we plot the corresponding distance from the origin. So we consider a vector that makes an angle of t with the horizontal axis, and as the angle increases, the r changes. So at some point we will see animations, and this can be made more explicit on how one defines polar coordinates. Spirals, for example, are very naturally defined in polar coordinates. The circle is r equals 1, a very simple equation in polar coordinates. Okay, so this is of course in symbolic computation. So we compute expressions. So given a curve, so we will show this on the curve invented by Watt. We have an equation and two variables, and then we transition into polar coordinates by going to the radius and angle variables, the r and the t, by substituting into replacing the x by r times cosine t and the y by r times sine t. So that gives then a new expression in the radius and the angle. We want to something of the form r equals a function of t. So we can ask to symbolically solve this. So we can solve one equation and write one variable in terms of the other. So that corresponds, by the way, to a factorization. We can make the solver work better if we simplify first using the trigonometric identities. For example, cosine square plus sine square equals 1, as you may remember from pre-calculus. We will see the components of the curve. So the symbolic factoring has a geometric interpretation. We see all the components of the curve and we isolate the difficulties. In particular, we will see that the origin, one isolated point, actually drops out. Okay, 4 different plots, 4 types of plots. The documentation of any scientific and symbolic software system can be very extensive, but here we narrow it down to 4 different types of representations for planar curves. Okay, so let me then swap the slides for the Jupyter notebook. So I have prepared a session and I will walk through the main statements in an interactive notebook. So let me make a new notebook with SageMath. So, and this is, by the way, the first lecture on a new chapter in this course. So in this lecture, we consider 2-dimensional plots. In this chapter, we consider essentially problem solving. So we are using SageMath to model and to solve equations. So the modeling is via the geometry. So in the plotting for today, the focus is that we consider 4 types of 2-dimensional plots. So there will be 4 subsections, starting with the graph of a function. So in this first type, we are given an explicit formula. So it is properly a function. Y depends on x. We are given a function and we use plot to make the graph of this function. So the graph by the function, which is defined by all the tuples x and y, where we can choose the range for x independently. So what was our example again? So we had a periodic function with a decaying amplitude. So unless you have seen this before, it's kind of difficult to visualize this. So let me make the plot, and I will separate the computation of the plot from the rendering. So we will plot the expression. So it's an expression in x, and I let x go from -2 to 2, and that's it. So I have the plot. So we can separate the statements. So the first thing that happens is that the plot gets computed and then it gets rendered. So I will use a smaller figure size so everything appears on the rather small figure window that I'm using here. The advantage of separating the computing of the plot with the rendering, so the showing, is that I can add to this plot. So let me add the two amplitudes. So I have the plus part, which is the plot of the exponential with the plus sign. I will pick the same range, of course, and display it in red. So I have now the plus, and I can show the original PF plot and add to it the plus plot. So that makes the positive part of the amplitude. To make the plot more symmetric, I will now type in the instructions for the negative part of the amplitude, and let's color this in green. So I have now my complete first plot. Okay, y equals f of x. So there may be problems, so let me look at a more complicated, or actually a less complicated recipe. So let me make the plot of this function. So also for x between -2 and 2. But you see that the 0 is a root of the denominator, and that will give problems. So you see that the plot is actually not so interesting. So this is a function that is not defined, and the plot results in 3 spikes. One at the origin and one at -1 and 1. And you see that the spikes are not even at the same height. So it's not a nice plot. I can make this better by providing ranges. So this goes all the way to -infinity and +infinity. For the value of y, of course, we cannot go to infinity. So I can give a minus value. So let me be modest, -4, and a maximum value, +4. And you see that then the plot looks a lot nicer. So you can see the parts in the plot. We have the asymptotes that are now drawn nicely at -1 and 1. But of course it's a wrong plot, because these vertical lines, they are not really, they shouldn't be in blue because they're not part of the plot. We can still make this better by asking Sage to show the poles. And that's done with a specific directive. So I will retype everything. So this is done with the detect poles, and I give the argument show because I want to see the asymptotes properly displayed. So this gives a much nicer plot of this function, which has 2 roots in the denominators. So if you have a rational form, the roots of the denominator are called the poles. Okay, this was the first type of plots where we have a graph of a function. Now I have the plotting of equations, so these are called the implicit plots. So with an implicit plot, we are given an equation f in two variables. So let me define the two variables. So the x is by default defined. I don't think the y is. And I will use the curve attributed to James Watt as our running example. So I will go to the prepared notes and copy and paste. In that way I do not make any unnecessary errors. So this is the curve which I will call Watt, and now I will do the implicit plot of the function, the equation, and now I have to provide ranges for x and y. So not knowing any better, I will again use -2 and 2. Although you see at first instance I better have taken -1/2 and +1/2. The other issue is that it's rather unclear. There is here this origin. So the point that I want to make is that, before I forget, is that if you replace x and y by 0, then obviously the origin satisfies the equation. But as a point, we can't really see it. Now, what could have happened is that the equation was too difficult to plot. And let me show how you can improve on a plot. So I will do implicit plot again. And now I will narrow the range a little bit, so I can take 1.4 minus 1.4 and 1.4. Fortunately, the curve is symmetric, and I can ask for 2000 points. The 2000 is kind of arbitrary. You see it takes a little bit longer, and I also have a nicer result. So the question now again is, why don't we see the origin? So looking from the plot, you would not think that the curve passes through the origin. And we actually don't know. Perhaps if we take 20,000 points, the curve will go through the origin. Okay, so curves given by or defined by equations are very interesting, and one can look at very nice shapes, but they are the hardest ones to plot because of issues with isolated singularities, like in this case. And we will see that also the curve, so the curve is of degree 6, actually not so high degree, that this curve, let me verify this, is indeed of degree 6, that this curve has multiple branches, so there is also the multiplicity. Let me save that and go to the third type, and these are curves given in parametric rectangular form. So in parametric form, we are given two functions, x of t and y of t, which define the values of the coordinates x, y, on the curve for some range t. Again, it could be that these two functions, they do have poles. There could still problems there. So finding then the good range for the parameter could still be an issue. Let us look at the Lissajous curve. So I'm using the parametric plot. So plotting the sine of 2 times t. So essentially I'm plotting tuples, and I have to give a range for sine and cosine. The natural range is 2 times pi. Okay, I was too quick. My t was not defined. So let me define it. And here we see one example of a Lissajous curve. So if you want more examples, you play, and more complicated examples, you play with these 2 and the 3, and throw also in a cosine, and you can also multiply the sines with each other and make very complicated looking curves with simple recipes. Okay, so let us now move to the fourth type. This is the type of the polar coordinates. So to plot a curve in polar coordinates, we are given an expression for the radius, and we use the polar plot. So this is our fourth type. Perhaps let me, before we immediately go into the more difficult curves, so let me show an example of a curve. I have to define, of course, the r, and perhaps let me, for completeness, also redefine the t. So I have my function of t, which will be r to the power 2. I'm now curious what this plot looks like. So which is essentially saying that as far as my angle is growing, the radius is growing. And here you see that the angle starts at 0, and we start at 0 as well. So for t equals 0, r is 0, and then we move with the radius. The radius actually increases, grows with the distance, with the angle. So a spiral is very naturally defined by the polar coordinates. Okay, so let me continue with our problematic function of what. So we consider the transformation of a curve defined by f of xy into polar coordinates. So what we have is we have the formulas to transform. So what is the input? So here is my equation, and in polar coordinates I have to transition So here are the transition formulas from polar, so polar R and T, into rectangular X, Y are given by the following. We have X equals R times cosine of T, Y equals R times the sine of T, where R is the distance, or the length actually, of the vector, the length of the vector ending at the point x, y. So it's the distance of the point to the origin, and t is the angle that vector makes with the x-axis. Okay, perhaps I should have started with that explanation, but we need these formulas now in transitioning from the rectangular to the polar. So you can read these formulas from left to right, and that's what we're essentially going to do. So we're going to replace the x by r times cosine t and the y by r times sine t. If you read these formulas from right to left, then the transition from the angle and the radius is also defined like by this. So I have my polar representation. So now we do some symbolic computation again. So I'm going to do a substitution. So we also call this a symbolic evaluation. So we have symbolic functions that are essentially replacing the letters, the undeterminate, the two variables in the expression. So here it is. It looks complicated, but if you remember your trigonometric formulas from pre-calculus, then you see that cosine square, sine square sits in there. And this may then get simplified. So I will simplify the formulas by asking Sage to apply the trig simplify to it. So the trig simplify will apply the trigonometric identities to it. And you see that now it actually simplifies a lot, because I have a curve. I have an expression of degree 6, so we have r to the 6 sitting in there, and a sine of t. So it's a curve of degree 6, and normally this won't factor. So for arbitrary curves, you can't really factor that well, but it actually does. And the symbolic solution is to see this again as an equation. So let me explain what I'm trying to do here. So we were given an equation, and we deduced, or we computed, another equation, but now in the r and the t. So if you wanted to solve y function of x, this did not work, but in this case we can solve g, that function, for r, and thus express the radius as a function of t. So it's probably not clear why this is going to work. We could have well tried to solve y in function of x. But for this particular example, the r in function of t works quite well, because in polar coordinates it's quite straightforward to deal with curves that pass through the origin. So the origin is kind of a specific point. Okay, so let's solve this equation, the simplified equation. Let's solve this for r. And oops, this went fast, but again, it's kind of intimidating. So what do we see? So let's stare at this a little bit. What we see, what pops out, at least to me, we have that the last component is r equals 0, and I could also compute. So we had a curve of degree 6, but we find 5 components. The solve actually did not take into account the multiplicities here, or the output does not show the multiplicities. But the origin will appear as a double point. So the first thing that comes out of this is that we see from the r equals 0 that 0, 0 belongs to the curve. And the other point is that the expressions look a lot complicated, look actually too complicated. If you would have to craft this by hand, it would be quite hard, I suppose. But the other point is that, and actually the main point is that the double point has been factored out. So now actually we get simpler equations, although it's not quite clear. So let me select the first component, and these are equations. So I'm selecting the right hand side. So here we go. And so now this is an expression in t that I can plot in polar coordinates. So you have to do polar plot. And the natural range is 2 times pi. So this is the first part of the plot. So let me assign this, and I will render this with show. So let me decrease the figure size to 3. And actually, the origin is kind of important. And let me remove the 2 axes. So, and again, I wanted to do too much. Okay, so the axis needs to be then defined. Let me do one more thing. Okay, so first the fixed size equals 3, and it's actually the polar plot that seems to be wrong. It got an unexpected keyword. How could that be? So I have an expression in t. So f naught is in t. And that copy it. Oh, of course. So I was reassigning the polar plot. So here we are, and I can remove the axis. So that's one of the factors, and actually this factor tells it all. So for completeness, I must continue. So let me continue with this. So I'm going to select now the next component, and I will do everything all at once. So I will make the polar plot, and let me use another color because I'm going to add both of them. Do the show with the fixed size equals 3 and remove the axis. Right hand side. So if you want to do too much, so and it shows up as kind of a purplish, means that both curves are indistinguishable. So this shows the multiplicity. So the curves defined by R F1 T and R F2 T are identical. So this is a double factor. This is another complication of this curve. So let me, for completeness, continue. So just to indicate that if you do the polar plot here, so now I hope I will not mistake. So I will call it green, and now do P0 plus P1 plus P2. So this becomes rather boring and repetitive, but this exercise has some more surprises. And here you see what happens. The plotting failed. And now it's interesting to look at the separate components. So splitting a cell is often good if you run into troubles. So see what happened. So this statement went fine. Let me look at the expression for F2. What do we see? We see one big square root, and the square root is an expression in the sine. So it's actually a polynomial with square roots in there, and I see negative expressions. If I look at the other ones, well, I also saw the square root. But the problem is that, and I will illustrate this, that the problem with this component is that the range for T causes problems with the evaluation of the square root function. Okay, so what's the problem? So let me illustrate this. I will evaluate F2, 2 times pi divided by 10 at 10 points for k in the range 10. So I have my parameter k. So k runs from 0 to 9, and I take a very coarse sampling grid, and the proper way to do this is like this. And let me numerically evaluate pi. Then you see what happens. The numbers are actually pure imaginary. So this is imagined. So this means that this component has not really a good representation. So the third component of this solution cannot be represented over the reals as a real plot. So in a later lecture I will try to explain how you can make complex plots. And the same happens for the third component. So let me also now do the last component, or the component that will be labeled 3. Well, the last component is the point, essentially. So I select the right hand side, and I will do the same to show that also here the square root is evaluated at negative numbers, and they are complex conjugates. So this was, after all, an algebraic. So we started with a polynomial, and all the roots appear, if they are complex, they are conjugated. Okay, what does this buy us? Well, I had my first, so let me now make the plots that I showed on the slides to conclude. So I had these two parts here, so I can still separate this. So let me illustrate the ranges. So I can let the range go from 0 to pi. And then I have the second part, is the polar plot, where the range goes from pi to 2 times pi. And one gets in this way. So let me draw them in complementary colors, one red, one green. So we have in this way two parts of this plot. So this in some sense factors out even more. So we can take this curve in apart. And there's one last thing that I need to do to make the plot complete. I must draw the point, the origin. So in a way this is a little bit a bad plot, so because you can't really see a point has dimension 0, so that's why I blow it up. But just for pedagogical purposes, the point is shown as a disk. So strictly speaking, from a geometric perspective, this is not a correct picture because you can't really show a curve, a point as a disk. But just to emphasize that there is something more than just the green and the red part. Also indicating the trouble when working with real parts of algebraic curves. There may be isolated points that one might not geometrically expect. Okay, the conclusion of this lecture: 4 types of plots, and we can, with symbolic computation, reformulate the expressions to examine the curves and to obtain more efficient plotting and more accurate plots as well. Okay, I hope this was interesting. I stop this recording now.